Okay, so now what happens if we have competing reactions that are both first order? So we're going to start out with one reactant, substance A, and it could go to product C, or it could go to product D. Well, for the reaction going from A to C, we have the rate constant K1, and going from A to D, we have the rate constant K2. So these two reactions are competing with each other. So we're going to say both are reversible and both are first order. So for a real life example, this is how it could be. We have toluene, and then of course in a catalyst of what is this? Nitric acid, and then H2O4, whatever that is, I don't even remember. But anyway, so it could be the orthoisomer putting NO2 right here, or the para-isomer putting the NO2 across from the methyl group. So we have the derivative of the concentration of A with respect to time. It's going to be equal to minus K1 times the concentration of A minus K2 times the concentration of A. And that's going to be equal to minus K1 plus K2 times the concentration of A. So now we're going to have A is equal to A naught times e to the minus K1 plus K2 times T. And that's going to be the integrated rate equation. So we have the derivative of the concentration of C, one of the products, with respect to time, is going to be equal to K1 times the concentration of A. So it's going to be K1 times the initial concentration of A times e to the minus K1 plus K2 times T. So we're going to separate the variables. So we're going to get the differential of concentration of C. It's going to be equal to K1 times the initial concentration of A times e to the minus K1 plus K2 times T with respect to T. And then we can integrate that. So we have the integral of the differential of the concentration of C is equal to the integral of K1 times the initial concentration of A times e to the minus K1 plus K2 times T with respect to T. So we have concentration of C is equal to K1 times the initial concentration of A times all this quantity here, minus 1 over K1 plus K2 times e to the minus K1 plus K2T plus I, where I is an integration constant because that's an indefinite integral. So at T equals 0, we get the concentration of C is equal to 0. So we're saying we're going to start out with only the reactant A, not the product C. So that's how we're going to find the value for the integration constant I. So we set that equal to 0, and we get 0 is equal to K1 times the initial concentration of A times this whole quantity here, minus 1 over K1 plus K2 plus I. So solving for I, we just get 1 over K1 plus K2. Because K1 is not equal to 0, and A naught is not equal to 0. Okay, never mind. So remember, these are products, right? K1 is not equal to 0. A naught is not equal to 0. So for this to be equal to 0, this quantity has to be equal to 0. So that's how we were able to drop those off. So that's how we know that minus 1 over K1 plus K2 plus I is equal to 0. And that's how we got I. So the concentration of C is equal to K1 times the initial concentration of A times minus 1 over K1 plus K2 times e to the minus K1 plus K2 times T plus 1 over K1 plus K2. So we get the concentration of C is equal to K1 times the initial concentration of A over K1 plus K2 times 1 minus e to the minus K1 plus K2T. That's equation 1. Then we have concentration of D, the other product, the competing product. It's going to be equal to K2 times the initial concentration of A over K1 plus K2 times this whole quantity here, 1 minus e to the minus K2 plus K1 times T. We'll call that equation 2. So here's a graph of concentration versus KT. And remember, K is going to be K1 plus K2. So the concentration of A over the initial concentration of A, remember we're starting with pure A, so it starts at the top, comes down. And then we're starting with no C or D, so this should be the origin. I didn't quite draw that neatly. So we come out C here, and we come out C here. Now, to get rid of the units, we're dividing by the initial concentration of C and the initial concentration of D. This is the way I was shown to do it. Notice though that the initial concentrations are actually 0. So we're actually dividing by 0 there. I'm not sure how we're allowed to get away with it. I think technically you have to leave out the... Well, anyway, yeah, it's kind of suspicious. Anyway, and then in this example with C higher than D, we're assuming that K1 is equal to 2 K2. If they were both the same, the two lines would be overlapping. You couldn't see anything. Now, the initial concentration of C and the initial concentration of D can both be 0. So like I said, technically we're dividing by 0 then. We get away with stuff in chemistry that they don't allow in math. Anyway, so if we can divide equation 1 by 2, we get the concentration of C divided by the concentration of D is equal to K1 times K divided by K2. Now, if we allow reversible reactions, then we have C in equilibrium with A, so we had a forward rate constant and a reverse rate constant. And then, whoops, I forgot a D here. That might help. Okay, then we also have A in equilibrium with D, so we have the forward rate constant and the reverse rate constant. So that's why we had K1 and K2. Now we have K minus 1 and K minus 2. So another way to write that, we could have C in equilibrium with K1 and A in equilibrium with 2. So we have this here. So these are the rate constants, these are the equilibrium constants. Now if we have K1 over K2, is that equal to concentration of C divided by the concentration of A, divided by the concentration of D, divided by the concentration of A. The A's cancel out, so you just get the concentration of C divided by the concentration of D as time approaches infinity, so that you're almost at equilibrium. So dividing the formula for the concentration of C by the formula for the concentration of D for the reactive reaction simplifies to just K2 over K1. Now, one thing that's important is that you can have one product favored thermodynamically, but a different one favored kinetically. If K1 over K2 is much greater than 1, then the concentration of C is much greater than the concentration of D. Then C is favored kinetically, because it'll have a small activation energy. So that's the rate constants. Now, if the equilibrium constants, if K1 over K2 is much less than 1, concentration of D is much greater than concentration of C, so D is favored thermodynamically, because D is more stable product than C. So we'll learn later on exactly how, but you can control the reaction, or control the conditions that you do the reaction, and then you can select which product you actually do end up with. Okay, so let's say that we have hydrogen bromide, which is a very strong acid. So the intermediate is going to be at the very bottom of the dip. So 1,4 addition is favored thermodynamically because it has lower activation energy. But 1,2 addition is favored kinetically because the hump isn't as high. That's all for section 3.